The universe has always been one of humanity's greatest mysteries. For thousands of years, people have looked toward the stars, trying to understand the vast expanse that surrounds us. From ancient skywatchers to modern scientists equipped with powerful technology, every generation has searched for answers about how the cosmos works. Yet each time we believe we are closer to understanding it, new discoveries reveal that the universe is far more complex than we imagined. In recent years, advanced space observatories have uncovered observations that challenge some of our long-held assumptions about the cosmos. Among the most intriguing discussions is the idea that an enormous amount of starlight appears to be missing from distant regions of space. While some reports have dramatically described this as the disappearance of countless stars, the reality is far more fascinating and scientifically complex. Stars do not simply vanish without a trace. They are born, evolve, and eventually die through processes that can take millions or even billions of years. However, astronomers studying extremely distant galaxies have noticed that the amount of visible light reaching us does not always match theoretical predictions. In certain deep space surveys, there appears to be less observable stellar light than expected. This discrepancy has sparked an important scientific question. Is the light hidden, altered during its journey, or are we misunderstanding how the distant universe should appear? Much of this discussion revolves around one of the most sophisticated scientific instruments ever built. The James Webb Space Telescope was designed to observe the universe in infrared wavelengths, allowing it to detect objects that are too distant, faint, or obscured for many previous telescopes. By capturing light that has traveled for billions of years, Webb provides a glimpse into the earliest chapters of cosmic history. Soon after beginning operations, the telescope revealed galaxies that seemed surprisingly developed for their age. According to many existing models, these early periods of the universe should have contained relatively small and immature galactic structures. Instead, Webb detected systems that appeared larger and more evolved than expected. These findings encouraged scientists to revisit some assumptions about how quickly galaxies formed after the birth of the universe. As observations expanded, researchers noticed additional puzzles. Certain distant regions appeared to contain fewer detectable stars and galaxies than simulations predicted. Several explanations have been proposed. Cosmic dust may obscure large amounts of light. Early star formation may have occurred differently than current models suggest. Some distant objects may simply be too faint to detect with existing technology. Whatever the explanation, these observations continue to inspire active investigation. To fully understand this mystery, it is important to consider the nature of the expanding universe. Nearly a century ago, astronomers discovered that galaxies are moving away from one another as space itself expands. This realization transformed our understanding of the cosmos. Light traveling across these immense distances becomes stretched, shifting toward longer wavelengths in a phenomenon known as redshift. Redshift serves as one of the most important tools for measuring cosmic distances and tracing the history of expansion. Through these observations, scientists eventually discovered that the expansion of the universe is accelerating rather than slowing down. This acceleration is often attributed to a poorly understood component known as dark energy. Alongside dark matter, which influences the structure of galaxies through gravity, these invisible ingredients appear to make up most of the universe. Ordinary matter, including stars, planets, gas, and everything visible to us, represents only a small fraction of the total cosmic content. As the universe continues to expand, distant galaxies move farther apart. Some eventually become so distant that the light they emit can no longer reach certain regions of space. This is not because those galaxies cease to exist, but because the expansion of space increases the separation faster than light can bridge it. As a result, there are limits to what any observer can ever see. This creates an extraordinary situation. When astronomers observe a distant galaxy, they are seeing it as it existed in the past, often billions of years ago. The farther away the object is, the further back in time we are looking. Meanwhile, that same galaxy has continued moving through cosmic history and now occupies a much more distant location than where it appeared when the light began its journey. Because of this process, the observable universe represents only a portion of the entire cosmos. There may be vast regions beyond our observational horizon that remain permanently inaccessible. Even with perfect instruments and unlimited technological advancement, some information may never reach us simply because of how space and time are structured. This idea carries profound implications. The universe is not merely expanding in size, it is constantly changing what can be observed. Objects visible today may eventually fade beyond detection as cosmic distances increase. Future civilizations could inherit a sky containing far fewer visible galaxies than we can observe now, making it harder for them to reconstruct the universe's history. Despite these challenges, every observation provides an opportunity to learn more about our cosmic origins. Each photon arriving at our telescopes carries information from an era that can never be revisited. Every distant galaxy offers a snapshot of a moment long gone. For this reason, astronomy is not only an exploration of space but also an exploration of time itself. Scientists continue developing new observatories with greater sensitivity and resolution. These instruments will allow researchers to study faint objects in unprecedented detail and investigate mysteries that remain unsolved today. As our understanding improves, many apparent anomalies may find natural explanations, while others could reveal entirely new aspects of physics. The discussion surrounding missing stars is ultimately less about disappearance and more about perception. The stars may still exist exactly where they always have. What changes is our ability to detect their light across an ever-expanding universe. In many cases, what appears to be absence may simply be the result of immense distance, cosmic evolution, and the limitations imposed by the structure of space itself. The universe is not necessarily hiding its secrets. Instead, it is constantly reshaping the boundaries of what can be observed. With every new discovery, humanity gains a deeper appreciation of the immense scale of reality and the extraordinary challenge of understanding a cosmos that is forever changing beyond our reach. Despite these challenges, astronomers are far from giving up. In fact, some of the most exciting discoveries in modern science are emerging precisely because observations do not always match expectations. Throughout history, major breakthroughs have often begun with a simple discrepancy, something that appeared out of place, something that existing theories could not fully explain. When scientists examine the distant universe, they are not merely counting stars or galaxies. They are reconstructing a cosmic timeline stretching back nearly 14 billion years. Every observation acts like a fragment of a giant puzzle. The difficulty is that many of those fragments have been distorted by distance, time, and the expanding fabric of space itself. One of the biggest challenges involves something known as cosmic redshift. As light travels across immense distances, the expansion of the universe stretches its wavelength. Light that originally left a galaxy as visible radiation can arrive at Earth as infrared radiation billions of years later. This transformation means astronomers must use highly specialized instruments to detect signals that would otherwise remain invisible. Even with the most advanced technology available today, there are limits. Some galaxies are so distant and faint that only a small fraction of their light reaches us. Others may be hidden behind enormous clouds of cosmic dust that absorb visible wavelengths and re-emit energy in different forms. In some cases, entire populations of stars could exist within galaxies that are simply too faint to observe directly with current instruments. This raises an intriguing possibility. What if much of the universe's missing light is not truly missing at all? What if it exists beyond the sensitivity of our current observations? Many researchers believe this explanation may account for at least part of the discrepancy. As telescopes become more powerful, previously invisible objects often emerge from the darkness. History provides many examples. Entire classes of galaxies once thought rare turned out to be common once better instruments became available. Objects that appeared absent were often waiting just beyond the limits of detection. However, there is another possibility that captures the imagination of both scientists and the public. What if these observations reveal that our models of cosmic evolution are incomplete? Modern cosmology has achieved remarkable success in explaining the large-scale structure of the universe. Yet even the most successful theories contain unanswered questions. Dark matter remains invisible despite decades of investigation. Dark energy, believed to drive cosmic acceleration, remains one of the greatest mysteries in physics. Scientists can measure its effects, but its true nature remains unknown. If our understanding of these hidden components changes, the consequences could ripple through every aspect of cosmology. Galaxy formation, stellar evolution, and the distribution of matter across the universe could all require revision. Some researchers have proposed that early galaxies may have formed stars much more efficiently than current models predict. Others suggest that unknown physical processes may have influenced the behavior of matter during the universe's first few 100 million years. While these ideas remain speculative, they demonstrate how observations continue to challenge established assumptions.